Today I want to talk about some work I've been doing in retirement. It involves using a side-looking ADCP, a horizontal ADCP, to measure discharge on a continuous basis. What I'll talk about, first of all, is some background information because it's key to understanding why this system was developed. And it relates to the Lake Michigan diversion and the computation of flow. And then we'll talk a little bit about why develop this system, QTrack System as it's called, and what is it. And then we'll talk about how we are computing discharge and the evaluations of that discharge computation, at least to date, and possibly some considerations for future work. I want to mention one thing first, is that there have been in the past at TMTW, or prior to that, ADCPs in action, at least two presentations that I'm aware of. I know one of them came from Korea. I do not remember the name of the researchers. And I think the other came from Japan. I'm not 100% on that. But they were doing something similar. And although I didn't develop this system, I pretty much suspect that that's where the idea came from originally. So I want to make sure and acknowledge that. So some background information for you to begin with. Originally, in Illinois and Chicago, this is present-day Chicago in this region here, there was a subcontinental divide in which water from this side to the east flowed into Lake Michigan, and waters to the west flowed into the Des Plaines River, which becomes the Illinois River, and then flows into the Mississippi and Gulf of Mexico. And for reasons I'll just explain in a minute, in the late 1800s, a canal was created that took water from this is called the North Branch of the Chicago River and South Branch Chicago River, and transported it down this canal and eventually into the Des Plaines River. So it was an interbasin transfer of water. And just as a side note, the people who did the work in the canal, many of them went on to work on the Panama Canal. In some sense, there's a good argument to be made that some of the ability to do the Panama Canal was first kind of tried out in this setting, although, of course, it was a much smaller undertaking. The reason this diversion was done was that Chicago takes its drinking water from Lake Michigan. And the Chicago River used to drain into Lake Michigan. And in late 1800s, there was no treatment of wastewater of any kind. And when they'd have a storm event, that water with all the sewage with it was carried out and into the lake. And Chicago has along its shoreline these things we call intake cribs. If you ever fly into O'Hare, the chances are you might see these because you usually land from east to west and fly over downtown Chicago. And if you looked out the window, you'd see several of these kinds of structures dotted along the lake. The original solution to this pollution problem was to keep moving the intakes further and further out. But it was a really severe health hazard. Today we get worried about 5 or 10 people getting sick from some sort of disease that's carried by water. There were massive numbers of deaths as a result of typhoid and cholera outbreaks tied directly to this problem. And so this is why the diversion was made. So the flow was carried down what's called the Sanitary and Ship Canal. But eventually, because so much water was being transported down this canal, there was no regulation initially of the flow, and there was upwards to 10,000 cubic feet per second being transported there. Various Great Lakes states sued the state of Illinois to regulate the diversion. Missouri, by the way, is not a Great Lakes state. The Great Lakes states were concerned about what would happen to the Great Lakes themselves, and that's why they sued. Missouri sued for a different reason. They didn't like getting Chicago sewage, so that was a big deal to them. As a result of these various lawsuits, in 1932, there was a U.S. Supreme Court decree that regulated how much water could be diverted. That decree was amended a number of different times, and the final amendment was in 1980. And among other things, that decree limited the mean annual discharge to 3,200 cubic feet per minute. That's about, I think, 91 CMS. And it required accurate accounting for the flows that were being transported down that system. In other words, they had to be unbiased and have a relatively low random error. In 1984, first of all, the original computation of discharge for this to answer the Supreme Court decree was done by computing flow through this structure, and there's one other upstream. It was called Lockport Powerhouse and Controlling Works. Consisted of hydropower system for generating electricity. There's about 40 feet of fall across that structure. A navigation lock, some sluice gates shown here, and then there's another set of gates up here somewhere. But in 1984, the USGS got involved in installing an acoustic velocity meter, which is a time of travel system. And this system became the primary means of computing discharge. It was set up with a 4-path system that it crossed the river like this, and there was one cross path, and they were at basically 3 different elevations. The cross path was at the same elevation as the middle path here. With this development, USGS became the primary supplier, if you will, of discharge measurement or discharge records for this diversion. And one of the outcomes, which we learned later on after collecting some data, is the big surprise: the state of Illinois was underreporting the amount of flow that was being diverted. And that was pretty important. So the place where I'm going to talk about our instrumentation today is located about, I think it's 11 miles upstream of the controlling structure I showed before. It currently has a 3-path time of travel system, a channel master ADCP that is on the canal wall. It will be on the right bank over here. And a number of other different instruments. There's an upward-looking Rio Grande, actually, in the bottom of the river, located a little bit upstream. There's temperature and specific conductivity strings, motion-activated camera. This is the most highly instrumented gauge and probably the most expensive gauge, I think, operated by USGS. And the upshot of this is that using the channel master now, we are using that as our official source of record, and we're computing continuous records of discharge, and that is being done using what we call the index velocity method. So anybody who's not familiar with that, I'll just say a few words about it in just a minute, but before I do, this is the equipment setup. One of the things that you can see here, it's quite expensive to do, is we had to cut a notch in the canal wall, and all these things here are part of our instrumentation. The QTrack system is located right here, just for your information. So the index velocity method is one in which we measure velocity in some portion of a river, and we use that as an index of the mean channel velocity. It's much like a thermostat in your house. Most of us have one thermostat in our homes, but we use that thermostat to regulate the temperature throughout the whole house. It's the same idea. And what happens is we have to develop, using the time series of velocity data from the side-looking ADCP, we also have a time series of stage data, and we make periodic discharge measurements. And using that information, we build what we call ratings, which are essentially some equations that describe the relationship between the index velocity and measured mean velocity. And the other one we do develop is a relationship between stage and cross-sectional area. So as it makes common sense, right? As stage increases, the cross-sectional area for that particular channel will increase and vice versa. And so we have ways of representing this, and simply once, if we have a stage value from our continuous record of stage and our index velocity, we can use that to compute a mean channel velocity and an area and discharge equals area times velocity. So it's very straightforward. So what is a QTrack system? And that's what I want to talk about mainly. So it collects discharge measurements, and we're going to call them measurements as opposed to a time series of computed discharge, during rapidly changing flow conditions. And this system works with a channel master mounted on a motorized track assembly. That's located right here. Here's a trolley for where the channel master is installed. The channel master is not there, but the mount is there. And this trolley is raised and lowered using a motor that connects to a chain inside this assembly. It also has a potentiometer. The potentiometer is used to measure the location of the instrument in the water column. One thing that point is important because we're not actually using channel master stage data at present to actually get the position of the instrument. So, and this is important because we want to check the instrument, check the position of the instrument. We have a Campbell data logger that's providing all the control for this system. It tells it where to go, when to measure, and so on. But because something could happen in this track assembly, if we say go to a certain depth, it may be that it doesn't go quite to that depth we desire, so the potentiometer gives us some sense of where it really is in the water column. The reason we use this system is because it's very difficult to measure during certain conditions. We have here an index velocity rating, so this is our time series, or our index velocity, and this is measured mean velocity from discharge measurements. And you'll see that when we get above about 1.5 feet per second, in this range here to 2.5, we have almost no measurements of any kind. And the reason for that is it's very difficult to capture that. That flow changes so quickly, it's hard to get there and get a boat in the water and actually make the measurements. And you see there's also a gap up here. And although we just have some measurements in this range, it's only very recently, and we've been operating this thing since 1984. So that's one reason. As a part of the Supreme Court decree, they didn't trust Illinois to do the computations correctly and account for flow, so they said that they had to hire a 3-member technical review committee, and this committee would meet every 5 years and review what's being done. And so one of these committees they always make recommendations about what needs to be done to improve the records and the computation process. And I want to focus on this second one here, where they talk about the understanding of unsteadiness in the canal. And particularly, they wanted to look at the evaluation of flow unsteadiness and what effect that had on computed discharge records, and what effect do barges have, because this is a canal where there's a lot of barge traffic. What effect do they have? And so the Illinois office of USGS has done a number of different studies to help answer some of those questions. This one here isn't directly answering that question, but it's a comparison of channel master computed discharges to the time of travel system. That was essential for us to use the channel master. We needed to prove that it's going to give us the same results. But this is first of 2 reports that looked at the effect of unsteadiness, and in this case, the potential for hysteresis in the index velocity ratings. And if anybody's interested in this subject at all, these are very, very nice reports. I had nothing to do with them, but the lead author, Ryan Jackson, is very, very skilled, and he's done an outstanding job of this. The third report that I don't show here deals with the whole question of unsteadiness and the effect of barges and actually density currents on our computed record. So what are the sources of unsteadiness? First of all, we have this controlling works downstream where you have power being generated, and there will be changes in the flow in order to accommodate the power generation. And it turns out that another source, and probably the biggest source of unsteadiness, is barge traffic. And you can see a barge approaching the lock here. And there's two ways. One is that the lock itself, when it's drawn down, when it's down and you fill it up, it causes a very sharp change in discharge. And I'll show you an example of that in a minute. This is a video of a barge going through the canal. If it goes. And this is derived from our motion-activated camera. And you can see here, this canal is about 49 meters wide, and this tow will occupy at least half of that width, and it will be about 3 meters deep. And the canal itself is about 7.5 meters deep. So this is an example of why we have to develop something because of the flow unsteadiness. Concentrate on this, I think it's a blue line here. I'm red-green colorblind, that's why I said I think. So you can see these very sharp changes. You can also look at this line here where we've taken out the trends because of major changes in flow. And you see these spikes up and down, and this has to do with the lockages that are downstream. And this is only a 3-day period or 4-day period. And you can see that these occur very common throughout, even on a single day. There's another source of unsteadiness. The barge traffic themselves, they actually generate at the gauge some changes in the velocity profile. So we have a downstream bound barge, and this is the typical velocity profile. This is from the bottom looking up. And this is the kind of normalized or normal profile for an upstream bound barge. Very different profiles, and they have an effect on the flow computations. And we had to evaluate what that was. Another reason for doing a QTrack system was that we have density currents at this point. Upstream of the gauge is another canal that comes in, and there's also thermal discharges upstream. And so what you have here is profiles for various kinds of flow conditions, and this is again from the bed looking up. You can see that there's very unusual shaped profiles, and what you see is the velocities near the bed increasing, which is not what you expect in a typical river system. And of course, above some point, they also increase. So you have this minimum, and this minimum is kind of where the interface between these density currents exists. So now, what are we doing to measure the flow? We have about 49 meters of width, and we have, that was supposed to be about, water depth is supposed to be about 7.7 meters. Yeah, here we are. And with this system, we're able to measure about 56% of flow. So the system normally sits at about 7/10 of the depth. And we keep it there unless conditions indicate some change in flow. And what we then do is increment the system, move it up in every 10th of the depth till we get to about 3/10 of the depth. The reason we stop there is because the canal stage can change, and we don't want to be measuring in a zone where we're getting side lobe interference or other things. It takes about 6 minutes to do this measurement. And we're computing flow doing two different methods. The primary method is midsection approach, where we divide the cross-section up into verticals. Anybody who's done stream gauging knows this kind of approach. And using 10 cells that are measured across the stream with the channel master, we can divide this up into 10 different sections. We have edges where we're not measuring with the channel master, so we have to account for those. And so the section 1 will include the measured cell which is extends to here, plus the edge. And the same will occur on the other side. And this is how we sample. And if you just, for example, for section 3, we take the width of that section, multiply the depth at that particular location, and we get the area, and then we average the velocities in this area here. We make at the present, no extrapolation to the bed nor to the water surface. I tried out a different approach, and that is a horizontal slice method in which we simply divide the cross-section up. So this is about, takes the top cell and we use that to represent all the water above it. And then we go down in tenths of the depth. And then again, from the last position, we represent the whole lower part of the water column. Again, we're not extrapolating, we're saying that the 7/10 depth represents everything down here, which may or may not be true. So what have we done to date? We've analyzed data from January 2018 to date. We filtered out data to remove obviously erroneous values. If we had any data that were invalid or missing, so if you think about 10 cells across the water column or at the various points in depth, if any of them were not there, we didn't include that in our analysis. The point was to try to do an accurate comparison. We were left with 2,100 measurements out of 5,000. And this is the result. Now, this slide here shows data where we compare the discharge from the QTrack system to discharge measurements. That means that we go out and make periodic measurements of flow. And so in a way, that is the ground truth of everything. Everything should be, that should be the standard. And so we're computing the percent difference here relative to these measurements. And there's some variation in the results, which we need to investigate. But our mean difference is around 1.5%, or if you look at the median, it's minus 1.2. I think that's quite good overall. If you plot this, the differences with a discharge instead of discharge measurement or time, you see that there does seem to be a little bit of a trend, and we only have 2 measurements at the high end, and we need to obtain more of those. The reason we don't is because we're only sampling at various points in time. If we detect a change in discharge, then we're activating the QTrack system, and that may not be the best strategy, which I'll talk about at the end here. This is another way of looking at the data where we have the percent difference, or sorry, this is a difference in discharge and then the published discharge. So these bar graphs is the published discharge and then the differences in discharge with time. And generally speaking, now we're comparing against the published record, not discharge measurements, but the channel master, which we said is a discharge record. It's kind of our official time series of computed discharge. And things look relatively good. If you squint at it, you'll notice that there is a little tendency to be a little bit of a bias on the high side or the positive side. If we look at the horizontal slice method, it's the same kind of story. There's very little difference between the two. And this is another way of plotting that, where we look at percent difference for the 2 methods, midsection and horizontal, and compare that versus the published discharge. You can see this more clearly, that there's a tendency to be biased a little high here. I'll skip that. So what have we learned so far today? First of all, the results are promising. If you focus on this alone, our discharge measurements, which is a standard for our project, that looks very good. If you compare it to the time series of published discharge, either using the midsection method for the QTrack system or the horizontal method, you can see that there tends to be biased a little bit high. It turns out that the reason for that is that in the CR6 Campbell data logger, they put in the width that was actually not quite correct. So it's actually, I think, is it wider? It's larger than it should be, I think. And so one of the things that has to happen is to adjust the discharges to reflect the correct area. So that's one thing we need to do. We also need to verify timestamps. So one of the issues there is that making sure that when you say initiate a measurement, that you have the timestamps on this Campbell data logger for the various observations are correct. Sometimes the unit doesn't move up to, say from 7/10 to 6/10 depth exactly in the time period we want it to. So there might be some issues there in terms of the length of our measurement and how that compares to our discharge measurements themselves or to the official record. Another area for concern and trying to investigate is how we are doing on the edges. So we have to watch out and look at that, and I have not spent any time on that. Some future work is we need to collect more validation measurements. Discharge measurements are the gold standard, so we have to do more of those, and you remember that the high end we only had 2 measurements, so we need to think about that. One of the things that we're focusing on is, can we run this thing on a continuous basis? The downside of that is that the more you use it, the more opportunities for wear and tear and the potential for the thing to break. So this is a kind of a delicate balance. We proposed doing this for an entire month to see if we can collect enough data to see if we have to operate it continuously or could we operate it at some discrete time interval. We need to develop more ways of screening out data that are more sophisticated. Modify the QTrack system to sample more smartly. Right now, the algorithms for kicking in the measurement and making it work are not very sophisticated at all. And we need to, as I've mentioned already, investigate the accuracy of the edges. If there's any time left, I'd be glad to answer any questions about this system and how it's...
Teledyne Marine. Everywhere you look.